This video is day 5 on regression, and we're working on example 2. So in this problem, we've been given spending in billions, and we have an input of years. When we go into Excel, you definitely want to always align your data first. So here, we've been given years 2008, 2009, and so on. I'm going to go ahead and align my data based on the year 2000. So I'm going to say X represents the number of years since 2000. So this 2008 will be represented by X equals 8, and 2009 will be X equals 9. So in Excel, I have copied that table, and I have inserted this aligned data for the X's, 8, 9, 10. Make sure you always do align your inputs so that you're not plugging in gigantic X values like 2008, 2009. In fact, if you try to do that and create an exponential regression model, it's going to overflow. You're not going to be able to accurately do that. So you need to align your data. All right, now this is going to be just like what we did with linears. I'm going to highlight the whole table, my inputs and my outputs, including the labels. I'm going to go to Insert, and I'm going to create a scatter plot for the actual data. I look at the pattern of behavior on my scatter plot. I see that I have an increasing concave up set of data. It seems to me that an exponential function would make a good model for this since it's increasing concave up. That seems like a good fit. So I click on one of the data points, right click, select Add Trend Line. And since I want to use an exponential model, I select the exponential model here. And remember at the bottom of the screen to have it display the equation on the chart. All right, I have my equation here. There we go. Lastly, click into the actual equation, right click, and format your trend line label. All right, when you click on this, we want to go into the area here for number, and I'm going to select number. I would like you guys to always be in the habit of having your equation with parameters listed out to 11 decimal places. That'll give us a lot of decimal point accuracy in Excel. So just by standard, go out to 11 decimal places, always uncheck the 1,000 separator. Now notice when I do that, the equation I have, that y-intercept value out front is now displayed out to 11 decimal places. We also see the rate in the exponential function. E is raised to this rate value here. It's also displayed out to a lot of accuracy. All right, so there's our equation. Let me go back and write that model into our Word file. All right, in Excel, we were given that model out to 11 decimal places, and I need you to get in the habit of writing in Excel and referencing values in Excel out to 11 decimal places. However, that it would be very tedious for us to continue to write 11 decimal places every time we reference the function. So when you actually write down your model and reference your model in your writing, you should only use up to 3 decimal places, please. Go ahead and stick with 3 decimal places when you write it down on your paper and make reference to those values. Again, in Excel, you use 11 decimal places for accuracy. On your paper, you can use 3 decimal places when you're referencing the parameters in your equation. Make sure also when you are writing down a model, you are very clearly identifying the meaning of the variables in your equation. So in this case, I'm using the letter T to represent the number of years since 2000. And I selected S of T to represent the spending in billions of dollars. Next, it asks us to graph the model. Notice it's asking us to just graph it on that same time frame from the original data, and it's asking us to use a smooth line curve. So in general, you guys are going to be given data sets like from real world data. You can take this data set and create a nice scatter plot like we did here that shows us the general shape of the data. We can use that data then to find a best fit regression equation. I then generally ask you to create a graph from your actual model equation. So you generally will have this, two graphs on your paper, a scatter plot from the original data, and then a nice smooth line graph using your model. Now to create this smooth line graph from your model, notice what we're going to be using from here on out is this equation. This equation is our model. You can copy and paste this down below into your Excel file so you don't have to type all those values out. I can highlight it and you'll notice that your right click copy is not there. If you right click, there is no copy. Instead, you can use the hotkeys on your keyboard, highlight it and hit Control C. Come on down to a cell and hit Control V and it will paste it in there. So then you can copy and paste the values. I'm just going to take this first parameter, which is the y-intercept, and copy that. And I'm going to label right above y-intercept is this number out to 11 decimal places. And then I'm going to come over here and write down the rate and copy and paste that value. There it is. Now we know that we can make reference to those values if we want to use them when we're writing our formulas. All right, next I'm going to create a new input-output table. It's going to look a lot like the original one from the actual data, but this time it's going to be based on the model. All right, so here I have the years again, and I've created those years into their new form, the t value, 8, 9, 10, 11. And now I'm going to use the model, the equation, to create these output values. So this cell will equal the y-intercept, so that's cell F13 for me, but I want to hold that constant, so I hit F4 times e raised to the rate, so that's this cell, I'll hold it constant, times the x value. Okay, again, notice I am using absolute cell references with a function f4 to hold the y-intercept and the rate value constant, and then we're referencing the cell to the left to get the x value. I'll drag that down. All right, and let's just quickly compare here. The model says at 2008 it's 22.24. The original data was 23.07, so that's not too far off. If you go down to 2014, the actual data was 54.956. The model says it's 54.30, so it's pretty good. You can see that on the graph as well. The graph of the little dotted line, which is the model graph, looks like it's pretty close to the actual data points. Now that I have an input-output table for the model, I can highlight the input-output and I can select smooth line graph, and there we go. The nice thing about this, of course, of having a model is that we can extend that. We could extrapolate. I could say, well, let's go up to 15 and year 16 and year 17, and we could create a model graph that extends out further. All right, part C asks us to identify the spending in 2015. So I've done that in the table here. I plugged in 15 and it says the value is 63.011,394.76. So that tells us in 2015 the spending was 63,011,394,760. So I took that value multiplied times a billion. Problem D says use the model to identify when the spending will reach 75,430,000,000. So first note, That would mean our S of t value is 75.43. I need to use Excel to have it identify when the function reaches a height of 75.43, when it has an output of 75.43. So I'm going to come back here to my input-output table. I see that it's going to happen somewhere between year 16 and 17. I'm going to put my cursor in one of those cells and use solver. So I click on that solver button. There we go. It says take this Y value cell, make it a value of 75.43 by changing the X value cell. I select solve, changes it for me. It says that happens at 16.2 years, 16.21 maybe after 2000. So 16.21 years after 2000. So a bit into the year 2016. Write a complete sentence to interpret exactly how the spending is increasing each year according to the model. So again, when I'm referencing and answering questions about this model, I'm going to use this 3 decimal places of accuracy. So I'm going to use this equation here as I wrote in part A. Okay, so this y-intercept is 6.766, meaning initially in the year 2000, this model predicts that the spending was $6.766 billion. And this 0.149 tells us that the function is increasing at a continuously compounding rate of 14.9%.